So I heard at least one yes. So whoever has seen it, what do scraper operations look like? No one wants to talk about them. Perfect. So we're going to cover over scrapers and look at what a scraper is and what scrapers are supposed to be doing for us, and how we can use a scraper to execute the type of construction that we want to touch. The first thing we're going to talk about is the anatomy of a scraper. What are the individual parts? And so the screen in front of you shows you a profile of a typical scraper. And this typical scraper consists of several parts. The first part here is the cab. In the cab, we typically will have an engine, we will have an operator, and we have the front axle. The second part is the bowl, and the bowl will consist of a banana link, an apron, a cutting blade, and an ejector. Each of these performs a different function. And then we have the rear end, which in this case is a set of axles, a fuel tank, another engine, and a push-pull bale. A hook is what it sounds like, and a bale is a loop like this. So if you imagine the handle of a bucket, that's a bale. These tools, loop, hook, and bale, allow you to connect two scrapers together for the purpose of providing additional power. Scrapers are able to do 3 different jobs, and to do them fairly well. The first is that it will cut. When we lower the bowl into the soil, it will cut and send soil up into our bowl, allowing us to fill soil in here. And that soil is collected by engaging the cutting surface of the bowl. When it is filled, the bowl comes up, this apron stays in place, and now we have a vehicle that is all set up to carry across the subgrade. So we have our soil in our bowl. We now drive to the point where the soil is being dumped. So if we have a cut area, we can cut with this piece of equipment, and we can then carry on and go into the fill with this piece of equipment. When it gets to the fill, we can lower the bowl and open the apron so that soil will flow out of here and be put down in a mat, the thickness of which we can control by our bowl elevation. So this is a process whereby we have cut, carried, now spreading the soil, and so our compaction equipment can come in behind and compact where our fill is going. So it's much like a a Swiss Army knife, or if you like, a Leatherman, a multiple tool. Does anyone have an Swiss Army knife or a Leatherman? And of course you probably do. And the lesson that you learn is that it does a lot of jobs, but it doesn't do any one of them particularly well. It's not necessarily the greatest knife. It's not a great pair of pliers. It's not a good screwdriver. It is not a good can opener. It's not a good wine bottle opener. It doesn't do any of those things very well, but it does all of those jobs in a workmanlike manner. So close enough, and you can get the job done. So the advantage to doing that is that scrapers do not require a lot of other pieces of equipment to operate with them. For example, we don't have a hauling vehicle and a separate loading vehicle and a separate spreading vehicle because they're all together. This gives us some real significant advantages. Those advantages being that the equipment can operate somewhat independently. We're going to find out not entirely independently, but certainly somewhat independently, and that it can cause all sorts of good things to occur. So our scrapers come in several different configurations, and each of those configurations is different in the way in which the vehicle is operated and in the way in which the vehicle is going to be loaded. The first and the most common is an open bowl configuration. In an open bowl, we have what it sounds like. There's a bowl that has nothing else in it other than space and the ejector. It lowers its tooth, or lowers the blade from at the front of the bowl and cuts into the soil. That soil boils up into the vehicle where it can be carried, and that's the term that we use, is boils, because of the shape, and then it can be carried. Now, it has to do several things with its engine. It has to push the cutting blade through the soil. It also has to haul itself across the site, and then it has to deposit. And so the amount of horsepower that's required to drive across the site and the amount of horsepower that's required to spread the soil is relatively small relative to what it takes to take the 7 or 8 or 9 or 10 foot wide blade and push it into clay and pick it up. So frequently, the vehicle is underpowered for filling itself. Where it's underpowered for filling itself, it needs a pushcat. A pushcat is a bulldozer or a tractor of some kind that can get behind the vehicle and give it that extra horsepower in the portion of the cycle that it needs to cut. If it doesn't need that extra horsepower in that cycle, or other ports in the cycle, it doesn't need that extra horsepower going down the road. It doesn't need that extra horsepower when it's dumping material, and it certainly doesn't need it when it's returning empty. And so we will see an open bowl vehicle very frequently operate with a dozer. That dozer is not moving the soil, rather it is picking up the vehicle by pushing on its rear and engaging the blade into the soil, providing that 20 seconds or 30 seconds of additional horsepower that's needed every 7 minutes. If you don't use a pushcat, you then have to have tandem loading or self-loading scrapers. A tandem loading scraper is a scraper that can act as a pusher for the vehicle ahead of it. And then once that vehicle is loaded, will come in and be pushed by the next vehicle behind it in order to help it load. So the vehicle is now doing a fourth task. It's not driving across the road, it's not cutting, it's not spreading, it's also adding additional horsepower while empty and pushing a vehicle to fill it. So sometimes those tandem scrapers can be one vehicle with two engines, one up front, one in the back. And often those vehicles can load themselves in loose materials, but will require a pushcat. A tandem push-pull is a vehicle that is able to assist its compatriots, its fellow vehicles in loading. If you're not using a pushcat or tandem scrapers, you then have two choices. One is an elevating scraper. An elevating scraper has a bucket elevator, we'll see pictures of this, that turns and picks up the soil and digs it out as the scraper moves across the soil surface. It has more moving parts, and it requires no pushcat. Similarly, an auger scraper has an auger that is inside the bowl, and it is what is doing the cutting with the soil to pick that soil up and to place it into the bowl. So any of these types could also exist as just a trailer that is pulled by a dozer or an agricultural tractor or a dump truck. Sometimes we see two or three together. So these are our types: an open bowl, which requires a pushcat, a tandem scraper, which probably requires a pushcat, tandem push-pull scrapers, which do not require pushcats, but the vehicle has to operate as a pusher, and then self-loading, elevating, and auger scrapers. And sometimes the scrapers do not have a tractor and are towed by a tractor. So that gives us our general overview. Now we're going to go into each one of them in a little bit more depth. This cartoon shows an open bowl scraper. Open bowl scraper consists of a cab element, forward element with the engine, this banana beam, which allows us to push down or raise the apron, this lever, which allows us to push the scraper cutting edge here into the soil, an ejector, which allows us to push the soil out, two axles, and a large cushion, which can be used by a pushcat to assist the vehicle and give it extra horsepower when it's digging in. So this is a conventional bowl scraper. It's the most common type of scraper. And here's one in operation. Decided to have some camouflage instead of safety yellow. This is the U.S. Navy preparing a naval air base somewhere where it's sandy soil. There's our scraper. Here's the cab with its engine. Here's the bowl. Here's the banana connector pushing and pulling on the apron. Here is the blade that is engaged in the soil, and it's filling the bowl up with soil. The ejector is in the rearward position because it is filling. Here is the rear end for the pushing, and here is a cat that is acting as a push cat with a push blade that has the shock absorber so as not to damage either vehicle. It's a pretty straightforward operation. The push cat pushes on the scraper. This tractor will pull the scraper across the road, but it needs this extra horsepower when it's being loaded. Of course, there are others. This is a tandem scraper. Tandem scraper because we have one engine here and we have one engine there, and each of these axles is driven by its own engine. The rest of the anatomy is similar. Extractor. This is our banana. Apron is here. Cutting blade is here. Here's the bowl. So this ejector can push this way and eject soil, or it is kept in the rear. The soil is at this elevation. The soil comes and boils in and fills the bowl up. We then raise the bowl so that it's sitting above the pavement or above the surface being cut. Could be pavement, it'll cut that too. Roll along, and then when it gets to the point of discharge, it opens the apron a little bit. It has a distance from the bottom of the bowl to the area where the fill is occurring, and this ejector pushes out in this direction, and we put out a layer of soil. And if you recall, when we talked about compaction, we talked about the thickness of this layer that was required to get compaction, and this is how we control it. In fact, we can go one step further. We can put a GPS system right here, and that GPS and a laser will tell us exactly the elevation that we're supposed to be filling at. So we can, to a very, very real extent, automate this entire process. And we get some, we really do get some decent performance if we try that. Here is a scraping operation with tandem scrapers. See the second engine in the back, the first engine in the front. Here are our GPS monitors. This vehicle, see the apron is up, this banana beam is up, which in this lever has pushed the bowl into the soil, and this vehicle is filling. You can just make out a little bit of soil right here. It's being assisted by its friend, who is pushing on the rear to give it that little bit of extra horsepower that it needs in order to cut the soil. Once this vehicle has loaded, it will drive away. This one will lift the apron, engage the bowl. A third vehicle will come up and push it, and it will start to pick up. And that is how a tandem scraper system works. They have this configuration which prevents them from sliding past one another and causing an accident. This is about a $10,000 tire, so I don't want this to hit my tire and prematurely destroy it. So I have a hook here and a bail. You can see the bail loops around the hook. They engage one another, and now we are not entirely free to move. And that helps immensely as we're going across the grade. So this vehicle in this case is acting as the pusher. This one is doing the cutting at the moment. But we'll see as we go along. All of these vehicles so far have to work together. The open bowl works with a push cat, and the tandems work with one another. This is an elevator scraper, very similar to what we saw before, except we have this bucket elevator, and it is basically 2 gears and a belt, and on the belt there are scoops, and the scoops move along. That's a horrible drawing. They move along, they dig up the soil, and then they deposit it back here inside of the bowl. There's still an ejector, and when we get to the point of placement, this can raise. The bowl would then drop at the right elevation, and the ejector will push the soil out, and so we'll leave a layer of soil behind. But these vehicles are much more expensive. They, in fact, they're considerably more expensive to own and to operate. So sometimes that can be good, sometimes that can be bad. This is a cutaway version of an auger scraper. We can see here's the standard cutting blade that the scraper has on the bottom of the bowl that is used to push through the soil. And then we have some additional cutting capacity with this auger. If this auger is operated in a clockwise manner, it pulls the soil in. If it's operated in a counterclockwise manner, it pushes the soil out. There's our ejector, which helps us to feed soil to the auger when we're depositing. But this piece of equipment will also self-load or load itself. So in the case of an auger or the case of an elevator, you don't need to work with any other vehicles, just the scrapers are in charge. The bowls can also be configured differently for different types of soil. The bowl consists predominantly of a space in which soil is carried and a cutter. This cutting edge is straight, this one is curved, this one is a 3-piece cutting edge, and if we go back up here, we also had a 3-piece cutting edge. These are used for cutting different types of soil, and the efficiency of each shape is very dependent on how compact the existing soil is and whether it's cohesive or non-cohesive and whether it's wet. So this 3-piece cutting edge is very good for cutting stiff clays. This curved cutting edge is very good for cutting fat clays, and the straight is very good for cutting lean clays, and so we can combine them. These are wear parts. They are going to wear out as the equipment is in operation in the same way that the shovels will, and I'll show you some, or same way rather that the blade of a dozer will. And I'll show you some photographs of what these parts look like when they're not new from the factory, because they don't keep that yellow paint on for very long. How does all of this work? It works on the principle of levers. We have 3 parts. We have a bowl, which allows us to engage or disengage the cutting blade. We have an apron, which allows us to open or partially close to control the spread of soil. And then we have an ejector. The role of the ejector is to push the soil out in this direction. The bowl lever can be engaged into the soil, or it can be used to spread, and the apron can move up so that there is nothing blocking the soil from boiling in here and filling. And so the way that this piece of equipment is used is it engages the soil either with its own power or assisted by another vehicle. It cuts that soil, it carries it like a truck would carry it, and then it goes to dump it on its own location. And there's an awful lot of operations that operate on this type of fashion, where we have vehicles that are doing more than one piece of work. The scraper cycle is very simple. We load with the bowl engaged with the soil. We raise the bowl, close the apron, haul across the site to a location where filling is being done, where we again open the apron, lower the bowl so that it is sitting above the soil, the thickness of layer of soil that we wish to spread, and we spread. And once that's done, we turn around and return to the cut. So just the way we had a soil or a cycle for the dozer, which was cut, carry, and spread, and return. Here again, we have load, haul, spread, and return. Similar type of cycle. The big difference is that because of the nature of the vehicle, it's able to go 35 or 40 miles an hour on a level haul road. When it can do that, it doesn't suffer from the problem the dozer had. What kind of speeds were we getting for dozers? Anyone? We were getting speeds 2 miles an hour, 4 miles an hour, right? So
Yeah.
once we were hauling a long distance, more than about 300 feet, the time started to be, our production started to be controlled not by the equipment, but by the distance it had to move. Because a D9 and a D10 and a D11 and a D12 will all go the same, about the same speed. So it doesn't matter how big the vehicle is when it's returning, but it sure does matter how big the vehicle is when you're figuring out how much it's costing to operate. And so we have that as a problem. Scrapers remove that problem by going across the haul road at much higher speeds. One of the ways that it does that is it does not rely on Caterpillar tracks, but rather relies on rubber tires. And so we are going to need to talk a little bit about rubber tires and the way that they work as opposed to the way that the vehicles would work with tracks. Now, there are some aspects of loading that we should be aware of. Backtrack loading is that the vehicles load in one direction, and then they head back along the line that they were proceeding upon. So they load in this direction, they head back along that line and turn. Sometimes you're in compact areas where you don't have a lot of room, or where the haul road and the working space are not quite close together. And so backtrack loading is something you would see from time to time. Similarly, shuttle loading is when you load in one direction and you carry in the other direction. So shuttle loading is used particularly in areas where it may be difficult to push the scraper. For example, if you're scraping, you ideally want to be level to downhill. Scraping uphill is no fun. So if you find yourself in a situation where you would have to scrape uphill, shuttle loading is something that may be done. Similarly, chain loading is done when you are able to load in the preferential downhill or level condition. And this is the most common to see. The pushcat gets behind the scraper, it loads, and then the scraper heads off. And there are a lot fewer turns, of course, because we're going to get better performance that way. Scrapers can do other jobs as well. One of the jobs you encounter in glacial soils is erratics, big boulders that have fallen out of the glacier. Those can be picked up by maneuvering, and anything of substantial size can be, as long as you can engage the cab around it, you can pick up a piece of soil. So you frequently see this because people like boulders on their property for some unknown reason. Often boulders are collected in one location and they're sold for a great deal of money. So in those particular cases, you want to be able to pick them up and move them without damaging them. Any other method of moving them will scrape them a great deal, but scrapers can lift them with very little damage. Let's talk about how we plan operations with our scrapers. Scrapers are efficient vehicles when they're moving straight ahead, and they're less than efficient in situations where you are moving them to turn. And so you want to plan your travel cycles in such a way that you are eliminating the turns. So let's take a look at A. In a project in A, we have a cut that is occurring in between two fills. We want to minimize our turns, so we set up a long loop. We cut in one direction, then we spread, turn, return to the cut, but don't turn back. Go from the cut to the next spread, deposit our soil, and then return. And so we have a loop that has two turns. The way you can increase the cost but not increase the efficiency of that operation is to cut and spread in a loop as shown on the wrong side. So you can see on the wrong side, for the same amount of work, we double the number of vehicle turns. If you have two cuts with a fill in between, it's the same concept. Do it so that you are spreading in a loop as in a continuous one long loop instead of two shorter loops. Why does this make a difference? Simple. Because a turn requires more time than running on a straightaway. And so a turn, we typically allow a quarter of a minute. Doesn't sound like very much time, except when you're running 6-minute cycles, now you've gone from 6 to 6.5, and you have decreased the amount of work you're getting out of each individual vehicle. You know, we've talked about dozers, you know, and dozers are expensive pieces of equipment. The D9s, D8s we've talked about, they're in the $250,000 range, $150,000 range. They're not cheap, but they look cheap if you compare them to scrapers. A 631K, which is a common scraper that requires a push cat that you will see in many locations, has a purchase price of about $2.7 million. And so you don't get production unless you've got 10 or 12 of them. So think of the capital investment. You have $27 million worth of scrapers. It's a lot of expense. The reason that we use them is that very frequently in road building and in site leveling, it's very efficient to use our scrapers in combination. So they're picking up, they're traveling 2,000 feet, and they're dumping it. We could try that with a dozer, but 2,000 feet will kill us. We could do it with trucks. We take an excavator, we load the truck, we drive the truck 2,000 feet, and then we spread it. That's also inefficient. So we're going to find out that from about 300 feet to about 5,000 feet, about a mile, scrapers are going to be cheap. We should always compare and make sure that we have the right equipment. But in that for 300 to 5,000 foot range, the scraper will almost always be the most efficient operation because you don't have as much handling. There's some safety aspects, of course, to filling. Where you're maintaining a fill slope, you want it to be concave, not convex, which means that you fill the alternate sides and then the middle, not in the middle all of the time. If you do that, you lose control of the slope when you're building it. In addition, it's not too hard to imagine what happens in a slippery conditions and in a moment of poor traction, is that scraper on the right is going to end up into the ditch. And you just know that OSHA is going to want to know why you rolled a very expensive vehicle, and your boss probably wants to know why his $2.7 million scraper is in the shop for $250,000 of repairs. If you operate as on the right side, you also lose control of the slope because it's very difficult to grade. In the left-hand side, if you have raining conditions, if it's wet, you need to have ditches and perhaps sumps to keep water out of it. Remember, most of the time we're going to be moving clay or cohesive type soils that are going to really like being wet. So we need to be aware of that. So let's take a look at the last type of scraper. This is a trailer. And this trailer is being pushed by a pushcat. It looks like it used to be an Army pushcat and still carrying the logo of the U.S. Army Corps of Engineers. But it doesn't have a forward tractor. It's attached to a Caterpillar tractor, which is at the moment operating as a just for its motive force. So in this particular case, we have a pushcat and a pullcat, and we can figure out how quickly that cat can move that scraper, because it goes about as fast as it would pushing the soil with a blade. So we don't see this type of operation with a single bowl very often. If you look up, this is the start of a project, not a lot of safety equipment in view, but you can see in the background there are open bowl scrapers being moved around. Those open bowl scrapers, there's 3 of them, right? 1, 2, and 3. Those open bowl scrapers are going to be using their work. They're cutting getting ready to cut, and you can see this cut marks from the bowl as the bowl is engaged. This cutting blade is here, the apron is up, and the hydraulic controls from this vehicle are controlling this cart. Of course, we have the right tractor with lots of motive force. We can have it haul 2 different vehicles. And you can see here where there's a little bit of rust that these vehicles are engaged in active work, so that you can see rust marks and you can see scraping here. So these are wear parts. This cutting blade often needs to be replaced, and the hydraulic controls from this tractor are in fact controlling the scrapers. And so this vehicle may do quite a bit of additional work, and you could figure out what is the loading characteristics, or what is the resistance to load, and figure out whether you have sufficient drawbar tie in order to keep things working. But this is the most conventional way to see a scraper job. You can see that this lead 631E has soil in the rear. This is the ejector back here. This is the apron is fully closed. This vehicle here is being loaded by the pushcat. This is where the cut is occurring. And this vehicle here is approaching the pushcat, ready to get loaded in turn. And so we have a cycle, which is each scraper has its own cycle, plus the pushcat has a cycle, and these 2 cycles become related to one another. The elevating scraper or self-loading scrapers, they can work alone, but they cost more to initially purchase and they cost more to operate, and it takes power away because the elevator takes power from the blade. This is a good cartoon showing the equipment in operation. Here's the cutting blade for the bowl. Here's the soil boiling up into the bowl. You can see that we have raised the apron to let the soil in. Once we're done, we close the apron, raise the bowl so that it is sitting above, and now it's just a truck, right? We've got this wheel here, it's being pulled forward, and we're hauling this soil away from the cut. Finally, we get to the point of spreading. We raise the apron. We still have the bowl. We set it to its desired elevation, so the thickness of a mat that we're going to put on, and the ejector is pushed forward, allowing us to move soil towards this cutting edge. So scraper operations are pretty straightforward, but they're different from dozer operations because dozers could theoretically work all by themselves. But most scraper operations are going to have several cycles. And let's take a look. Here we're loading. There's our scraper with a push cat. Drive along the road, does it all by itself, comes to the point where it's being dumped, where we have a dozer and it's assisting us in spreading and it's assisting us in doing some compaction. And then unloaded, we return to the point of loading and start over again. Here we have a dozer and we'd have compaction equipment consolidating the soil. And here, does anyone know what this cartoon is? It's a motor scraper. What is its job? To maintain the haul road. And we're going to find out that maintenance of the haul road or the condition of the haul road will control our production. It makes sense. If you don't have a good road, then your vehicle can't move as quickly as it possibly could, and therefore we will see some drop in efficiency. So we will have an exercise. We will look at it and we'll do a cut fill operation with scrapers with and without a dozer, or rather with and without a motor grader, and then we'll see which one is more productive and at what point and how long the haul road has to be before that motor grader pays for itself. I'm going to take a pause just for a moment and start talking about cycles a little bit before we go on any further. Okay, so just give me a moment here. We have a unique to us so far system now where the dozer cycle was pretty easy to understand. Right? The dozer cycle, we had push, we had cut, push, spread, and return. And it was pretty much, that was the way that it was, right? That was pretty much the cycle. We'd have a cut and return or whatever, what else have we? And that would be the end of that. But that's not where we are. Something else happening. We have our scraper cycle. So it's cutting, it's hauling, it's spreading, and it's returning. Just like the dozer. But part of the load cycle or the cut cycle is a scraper or there is a push cat. and it has to push and then maneuver. So the first operation is that it pushes the scraper to load it, but the second operation is it then maneuvers to engage the next. So this is a cycle. And this is a cycle. And then where we're spreading, we have a compactor cycle, just like we did in the midterm, right? And this is the number of passes that we need to make in order to get to the specified density. And so we have 3 cycles, and those 3 cycles work together. So what does this mean for our management and planning purposes? Is that we have a potential problem where our cycles are not always going to be as clear as they are. So I'm going to give you an illustration. Do you remember way back when we used to be able to go to bars? We would have, I'm sure some of you remember, we would have tables, there'd be people at them. Those people would be happy because they're at bars. And let's suppose that we have a situation where you're drinking lemonade. Because, you know, what else would you be drinking, right? We also had bar service. And they had a cycle. Their cycle is they go to the bar, they load lemonade. They haul the lemonade across the bar. They deposit it on your desk, on your table, and then they return. And then we have the publican or the bartender, and he is filling glasses of lemonade. And his cycle is that he fills, delivers to a tray, and then goes back and fills. So they also have a cycle. So there's a bartender cycle, there's a waitress cycle, and there's a drinking cycle. And these 3 cycles are all interdependent. But it leads us to an interesting problem. If you can drink black, right? If you can drink 20 glasses per hour of lemonade, and the waitress can deliver 12 glasses per hour, and the bartender can load 8 glasses per hour, we now have an interesting situation. If I have one bartender is 8 glasses an hour, 2 of them is 16, 3 of them is 24. I have a waitress, 1 of them gives me 12, 2 of them gives me 24, and then I have students, and they are drinking 20. So I have a bunch of paths that I could follow, right? I could follow path number one. I have one bartender, so I need one waitress who delivers 8 glasses per hour to the students. What's going to happen then? Right? There will be thirst. That's not good. Well, I could have 2 bartenders who fill 16 glasses an hour. I could still only have one waitress, and I haven't fixed my capacity. I'm still only delivering 12 glasses per hour. I still have disappointed students. Can't draw students today. So I could also say, well, I've got 16 bartenders, 16 glasses because I have 2 bartenders. I could give this to my 2 waitresses. They have the capacity to move 24, but they're only getting 16, so they deliver 16 glasses. I'm still not so happy. I'm not quite as mad as I was, but I'm still not happy. Could also do this. I could take 3 bartenders. They load 24 glasses. They send those 24 glasses to the students, who then get 24 glasses through the waitresses. So I have 3 bartenders, 2 waitresses. Now they die of lemonade poisoning because they can't drink 24. Eventually, they end up being unhappy and bad things happen. Right? So what would I actually do is I would say, well, I've got 3, but I'll load 20. So the bartender waits. It will give them to the waitress or the servers, who will move 20 to the students, who will be happy, probably. Depending on how we're doing, the bartender could control production, the servers could control production, or the compaction could control production. Compaction is the easiest one to deal with, so rarely will we let compaction control production. So we had 2 situations here. We would get 24, but we could make 24, but we'd only load 20. We'd have 2 waitresses carrying 20, and we would see how we're going. In that case, the only people who we have, the waitresses that are idle sometimes, we have bartenders that are idle sometimes. If we go to making 16 drinks and we have a waitress that delivers 12, well then we could end up in a situation where the waitresses are idle a lot, but the bartenders are busy. In each of these cases, one of the cycles controls production. When we go through our pushcat dozer cycle combination, we're going to find out that we won't have an exact match. There won't be use 1 pushcat per 8 scrapers. It will be for every 8 scrapers, use 1.3471, whatever it is, 1.7 pushcats. I'm going to have to show you how to do those calculations. So if we have a situation where it calls for 4 pushcats, it won't be 4.00, it'll be 4.3. If we only have 4, then the scrapers are going to control production. If we have 5 pushcats, then the push cats are going to control production. And so we're going to be able to make a decision as to what's the value of the marginal vehicle. So in order to do that, we're going to have to run a time study, just like we did for dozers, but run them on scrapers. And in order to do that, we're going to need to be able to predict our scraper performance. This is a curve for a scraper. Just like it was for a dozer, a little bit more complicated because there's a little bit more moving parts. And a scraper is going to give us the ability to estimate off-site what the production is. So we've got a few things we need to look at here. We have two characteristics. This is, I think this is a 614K, but I don't remember, but it doesn't matter. Here we have the empty weight. Its empty weight is 98,000 pounds. Its loaded weight is 158,000 pounds. So somewhere in here is where your soil is going to be. We need to look at the loose density of the soil. We need to look at the bowl volume. We need to look at the fraction filled. Once we know what our weight is, we can come down and use this curve to determine several things. If we come down the weight until we hit the total resistance, and this is what we're going to talk about on Wednesday, the total resistance expressed as a grade, we'll encounter that line, right? We encounter this, these lines for different grades. In this case, we have a 10% grade. We intersect here, we read over till we hit a gear. And this gives us two pieces of information. The first is it tells us that it's going to be moving on this grade in fourth gear at a speed of 12 miles an hour. And then it also tells us that we need to have a rim pull available of 16, or we're going to have a rim pull available of about 17 or thereabouts pounds. So rim pull is a way of measuring the ability to take flywheel horsepower and apply that to rubber tires. So that's what we're going to start with on Wednesday. Once we know that, we can determine how quickly we can go and whether that scraper has the capacity to do so. On the return cycle, we have something different. This is a retarder. A retarder curve is using the diesel engine as a brake and exerting a back pressure on the vehicle. This gives us the rate at which it will naturally move with the engine in service. What it does for us is it allows us to calculate what our speed on return is. Very similar. Here's our gross vehicle weight, right? Empty and loaded. Here is the effective grade, which we're going to talk about on Wednesday. This is, let's suppose if we want to look at an example that's loaded, this particular vehicle has a loaded weight of 238,370 pounds. We bring this down until we hit the 10% effective grade. From here, we can read over and say, our vehicle is going to be in 5th gear and it's going to move 13.5 miles per hour on the way back with very little load on the engine. In other words, you're going to be going, this is assuming you're going downgrade. You always set it up so that if you're going downgrade, you would end up with a situation where the vehicle will move using almost no fuel. It'll at the idle type speed at 13.5 miles an hour. And so using the retarder is the most efficient way of using things. I think I had told you about electric cars or electric trucks that Caterpillar is using that use their gas engine to climb, but they use their electric engine to come down loaded. And very rarely do they need any gas going down. In fact, after they've gone up the first time, this loop allows them to they come down with the retarder, which generates electricity, and then they go back up with the electricity from the retarder. They never use fuel anymore. And we're seeing more and more types of vehicles that are coming into service that are using electrical systems. That's what I want to cover today for scrapers. This process that we're going through is ever changing, and I don't know. I'm not going to commit to that the university has sorted out exactly what's going on anyway. But what we're going to do as section 2 of heavy methods of construction for this semester is we're going to carry on doing what we have been doing so far. 3 hours of a lecture by anyone can be a little on the rough side. What is going to happen with this particular lecture is I'm going to translate it electronically into something that's that can be put onto the canvas, and so you'll be able to reference it. When we get going again on Wednesday, we're going to go through rim pull and motive power and how we determine the performance of wheeled vehicles that are operating using flywheel horsepower, and how to estimate the production that we will get out of a scraper cycle. What I've done in the past, of course, is we would walk through up on the board calculation. You can see even once I get my better pencil for working on the surface, it just is not quite the same thing. So what I'm going to do is I'm going to write out a problem and the solution, and then and have that on something you're going to be able to see. And we'll walk through those calculations, and then we'll have a question sheet. I see that many of you have been sending me your exams, which is good. It's a lot simpler when we have assignments to turn them in face-to-face. We're not going to be face-to-face for the remainder of the semester. As a result, we're going to get quizzes set up that are really assignments. You'll be able to do those assignments on Canvas, and that you will they will be somewhat self-grading, and we'll get up to speed with doing that. These lectures for an hour with not being able to hear or see any of your cheerful smiling faces making you drink lemonade are I'm okay with them, It's not quite how I would like to do things, but that's not where we are as a country or as a society at the moment. So I need some feedback from you. How much of this worked? Tyler, you are already unmuted. So how did it work? Okay, Zach, how about you? How did it work?
Oh, I didn't think it was that bad. I thought it went over pretty well.
Yeah, I mean it'll be a little bit more PowerPoint-ish, at least on Mondays. But what I want to make sure that we take away is that we can, just like we did for dozers and for compaction equipment, that we can compute for ourselves what the production will be. And so that's the next step. Conceptually, it's no different. In other words, it's going to be just like doing the dozers was. It's going to be just like the compaction equipment. And when we get to a different spread of equipment, which is shovels, hose, and trucks, by that time it will be old hat. But I want to make sure that I don't go too quickly, and I want to make sure that that everyone is following along.
Yeah.
We will also be able to, I'll be able to get you some recorded videos that show you how to do the calculations as well. But I think at the moment, at least for at least a few minutes, if not an hour, every class session, we should get together. If you're having any problems whatsoever with the university, not just with this class or anything else, and I can be of any assistance, you all have my phone number. You all have my email address. I'm sitting in the university. It's the creepiest place. I think there's about 5 people here. And so just like you probably wish you were here, I wish you were here as well. In particular, I miss the interaction with some of the, let's put it, more dubious, more doubtful members of society, of our class, so I can tell them what life was like as an engineer, so that you can be sure you don't want to be one. So we'll keep going, but I need any feedback you have, if it could have been better, if it could have been worse, if running a video camera and talking over the calculations works, which you'll see next. Just is a learning process for us all. I was talking to some other professors this morning after I ran the first heavy methods class. For me, it's like talking to a wall, and I find that more difficult than it should be. But it is important for you all to realize that the current situation, although completely unprecedented and unexpected and unplanned for by anyone, is a temporary situation. We will finish this semester with as much of the class as we can do finished, and with you confident in how heavy equipment operates. By that time, chances are that we will be back to some level of normalcy for our day-to-day operations. So if you have any questions, concerns, suggestions, ideas, I'm working on doing things maybe it'll be a little bit more fun. So than hearing me drone on. I mean, it's bad enough when I'm in person, but at least I get a joke out from time to time. Now it's just showing you pictures. So please send me any feedback, and that's what we've got for today.